Welcome back. Having seen correlation on a scatter graph, in this outcome, we put an actual number on it, meeting Pearson's coefficient for measured data and Spearman's for ranks, and learning which one to reach for. A scatter graph is a great start, but describing a relationship as quite strong is far too woolly for serious analysis. A correlation coefficient boils the strength and direction down into a single number, and every one of them lives between -1 and +1. We'll study two: Pearson's product moment coefficient and Spearman's rank coefficient. Which one you choose depends on the type of data and the shape of the relationship. Let's get a feel for the scale. An R of +1 is perfect positive linear correlation, every point sitting on a rising straight line. An R of -1 is perfect negative correlation, all points on a falling line. An R of 0 means no linear correlation at all. So the sign gives you the direction, and the size, how close to 1, gives you the strength. In between those extremes, the closer the correlation coefficient R is to plus or -1, the more tightly the points hug a straight line, and the nearer it is to 0, the fainter the pattern. As a rough guide, an absolute value above 0.8 is often called strong, around 0.5 moderate, and below 0.3 weak. But treat those as guides, not gospel. And always glance at the scatter as well. And a strong R still never proves that one variable causes the other. Pearson's ER measures the strength of a linear relationship between two quantitative variables. The formula is R equals Sxy, divided by the square root of Sxx times Syy. Here, Sxx is the sum of x squared minus the quantity sum of x, all squared, over n. Syy is exactly the same idea for y. And Sxy is the sum of xy minus sum of x times sum of y over n. Because it uses the actual data values, it suits genuine measurements with a straight line trend. The routine has 4 steps. Tabulate columns for xy, x squared, y squared, and xy, and total each. Work out Sxx, Syy, and Sxy from those 3 sum of squares formulae. Combine them. R equals Sxy over the square root of Sxx times Syy. Then interpret, stating the direction from the sign and the strength from the size, and always adding a word of caution about causation. Let's build the table for 6 paired observations of x and y. We add columns for x squared, y squared, and xy, and total every column. That gives the sum of x as 21, the sum of y as 40, the sum of x squared as 91, the sum of y squared as 316, and the sum of xy as 168. Tidy tabulation like this is what stops silly arithmetic slips creeping in, and those 5 totals feed the 3 formulae. Now the calculation, with n equals 6, Sxx is 91 minus 21 squared over 6, that's 91 minus 73.5, giving 17.5. Syy is 316 minus 40 squared over 6, so 316 minus 266.67, which is 49.33. Sxy is 168 minus 21 times 40 over 6, that's 168 minus 140, giving 28. So R is 28 over the square root of 17.5 times 49.33, that's 28 over the square root of 863.3, so 28 over 29.38. which comes to 0.95, a strong positive correlation. So, what does 0.95 actually tell us? The positive sign says y rises as x rises. The size, right up close to 1, says the points lie very tightly around a straight line, so it's a strong positive linear relationship. But, and you knew this was coming, 0.95 still doesn't prove x causes y. What a high R does do is justify fitting a regression line to make predictions, as long as we report both direction and strength, and add the causation caution. Pearson isn't always the right tool, so check 3 things. Both variables should be quantitative, measured on a real numerical scale. The scatter should look genuinely linear, and there shouldn't be extreme outliers because they can distort AR badly. If your data is ranked, or ordered but curved, or riddled with outliers, that's your cue to switch to Spearman instead. Spearman's coefficient measures how well two rankings agree, and the key difference is that it works on the order of the data, not the raw values. That makes it ideal for ordinal data, things like judges' rankings, league positions, or star ratings. It also copes when the relationship is monotonic, steadily rising or falling, but not a straight line. And because it only uses ranks, it's far more resistant to outliers than Pearson. The formula is Spearman's coefficient equals 1 minus the quantity 6 times the sum of d squared, all over n times the quantity n squared minus 1. Here d is the difference between the two ranks for each item, and n is the number of pairs. Like every correlation coefficient, it stays between -1 and +1, where +1 means the two rankings agree perfectly, and -1 means they're exactly reversed. 4 steps again. Rank each variable separately, deciding whether 1 is the highest or the lowest, but staying consistent. For each item, work out d, the rank of x, minus the rank of y. Square each d and total them to get the sum of d squared. Then apply the formula 1 minus 6 times the sum of d squared over n times n squared minus 1. Let's take two judges scoring 7 competition entries, A to G. Each judge's scores are turned into ranks, with 1 for the highest score. Then D is the difference in ranks, and squaring it removes the sign. In this case, only entries A and B differ, each by a single rank, so the sum of D squared is just 2. Straight away, that tells you the judges are agreeing very closely. Now the arithmetic, with n equals 7 and the sum of d squared equals 2. First, n times n squared minus 1 is 7 times 49 minus 1, so 7 times 48, which is 336. Then 6 times the sum of d squared is 6 times 2, that's 12. So Spearman's coefficient is 1 minus 12 over 336, that's 1 minus 0.036, which rounds to 0.96. A value of 0.96 signals very strong agreement between the two judges. A quick practical note on ties. If two values are equal, they share the mean of the ranks they would have occupied. So two entries tying for third and fourth place both get 3.5. As for reading the result, near +1 is strong agreement, near -1 is strong disagreement, and near 0 means little connection. Our 0.96 means the judges rank the entries in almost exactly the same order, though even that doesn't prove one judge swayed the other. So, when do you use which? Reach for Pearson when both variables are numerical measurements, the scatter is genuinely linear, and there are no severe outliers like revision hours against marks. Reach for Spearman when the data is ranked or ordinal. The relationship is monotonic, but not straight, or outliers would wreck Pearson's R. The two judges example being the perfect case. Let's line the two up on the key questions. On data type, Pearson wants interval or ratio measurements, while Spearman handles ordinal or ranked data. On the relationship, Pearson needs it linear, whereas Spearman just needs it monotonic, any steady rise or fall. Pearson is sensitive to outliers, Spearman much less so, and the deciding difference is that Pearson works on the actual values, while Spearman works purely on ranks. It's worth hammering this home one more time. Whichever coefficient you use, a strong result only ever shows association. A confounding variable or plain coincidence can throw up a high number, and only a controlled experiment can establish genuine cause and effect. So the professional habit is report the coefficient, describe its strength and direction, and always tack on the causation caution. A number never upgrades association into proof. Here's it working in the real world. A coffee chain like Costa records each store's customer satisfaction score and its repeat purchase rate. Both are numerical, so they calculate Pearson's R, and it comes out around 0.8. A strong positive result, suggesting happier customers tend to come back more often. If instead, they'd only ranked their stores 1st to 10th on service, Spearman would be the right tool. Either way, they can't claim satisfaction alone causes loyalty, because price and location clearly matter too. Let's gather it up. A correlation coefficient turns strength and direction into one number between -1 and +1. Pearson's R, SXY, over the square root of SXX times SYY suits linear quantitative data, and our worked value was 0.95. Spearman's coefficient, 1 minus 6 times the sum of D, squared over n times n squared minus 1, suits ranked or ordinal data, and ours came out at 0.96. Choose Pearson for measured linear data, Spearman for ranks or outlier-prone data. And remember, a strong coefficient still shows association, not cause. And that completes our work on measuring correlation. If you want to solidify it, Roundtree's Statistics Without Tears explains coefficients without the heavy algebra, while Crawshaw and Chambers walks through the full Pearson and Spearman calculations. The Royal Statistical Society's Significance magazine is great for seeing correlation used and misused in real studies, and the Office for National Statistics site offers plenty of paired data to practice on. Corbett Maths and BBC Bitesize have step-by-step videos, and it's all linked on the Moodle for this unit.